Good morning, everyone. Glad you're all here bright and early. We're counting the days to when the TAs outnumber the students. They'll show up. We return to a familiar story. This is part 2, the Empire Strikes Back. So last time, our adversary, the graph, came to us with a problem. We had a source, and we had a directed graph, and we had weights on the edges, and they were all non-negative. And there was happiness, and we triumphed over the empire by designing Dijkstra's algorithm and very efficiently finding single source shortest path weight from S to every other vertex. Today, however, the Death Star has a new trick up its sleeve, and we have negative weights potentially, and we're going to have to somehow deal with, in particular, negative weight cycles. And we saw that when we have a negative weight cycle, we could just keep going around and around and around and go back in time farther and farther and farther, and we can get to V arbitrarily far back in the past. And so there's no shortest path, because whatever path you take, you can get a shorter one. So we want to address that issue today, and we're going to come up with a new algorithm, actually simpler than Dijkstra, but not as fast, called the Bellman algorithm. And it's going to allow negative weights, and in some sense allow negative weight cycles, although maybe not as much as you might hope. We have to leave room for a sequel, of course. Okay, so the Bellman-Ford algorithm, invented by two guys, as you might expect, it computes the shortest path weights. So it makes no assumption about the weights. Weights are arbitrary. And it's going to compute these shortest path weights. So remember this notation. Delta of S comma V is the weight of the shortest path from S to V. S was called a source vertex. S is in V. And we want to compute these weights for all vertices, little v. The claim is that computing from S to everywhere is no harder than computing S to a particular location, v, so we're going to do it for all of them. It's still going to be the case here. And it allows negative weights, and this is the good case, but there's an alternative, which is that Bellman-Ford may just say, oops, there's a negative weight cycle. And in that case, it'll just say so. So say a negative weight cycle exists. Therefore, some of these deltas are minus infinity, and that seems weird. So Bellman-Ford, as we'll present it today, is intended for the case where there are no negative weight cycles, which is more intuitive. It sort of allows them, but it will just report them. In that case, it will not give you delta values. You can change the algorithm to give you delta values in that case, but we're not going to see it here. So an exercise, after you've seen the algorithm, the exercise is compute these deltas in all cases. So it's not hard to do, but we don't have time for it here. So, here's the algorithm. It's pretty straightforward. As I said, it's easier than Dijkstra. It's a relaxation algorithm. So the main thing that it does is relax edges, just like Dijkstra. So we'll be able to use a lot of the lemmas from Dijkstra, and the proof of correctness will be 3 times shorter because the first 2/3 we already have from Dijkstra. But I'm jumping ahead a bit. So the first part is initialization. Again, d of v will represent the estimated distance from S to v. And we're going to be updating those estimates as the algorithm goes along. And initially, d of s is 0, which now may not be the right answer, conceivably. Everyone else is infinity, which is certainly an upper bound. Okay, these are both upper bounds on the true distance, so that's fine. That's initialization, just like before. And now we have a main loop which happens v minus 1 times. We're not actually going to use the index I, it's just a counter. And we're just going to look at every edge and relax it. It's a very simple idea. This is, if you learn about relaxation, this is maybe the first thing you might try. The question is, when do you stop? Sort of like I had this friend who, when he was like 6 years old, he would claim, "Oh, I know how to spell banana, I just don't know when to stop." Okay, same thing with relaxation. This is our relaxation step, just as before. We look at the edge. We see whether it violates the triangle inequality according to our current estimates. We know that the distance from S to V should be at most distance from S to U plus the weight of that edge from U to V. If it isn't, we set it equal. So we've proved that this is always an okay thing to do. We never violate, these d of v's never get too small if we do a bunch of relaxations. So the idea is you take every edge, you relax it. So I don't care which order, just relax every edge, one each. And then do that v minus 1 times. The claim is that that should be enough. If you have no negative weight cycles. So we need to, if there's a negative weight cycle, we need to figure it out. And we'll do that in a fairly straightforward way. Which is we're going to do exactly the same thing. So this is outside the for loop here. We'll have the same for loop for each edge in our graph. We'll try to relax it. And if you can relax it, the claim is there has to be a negative weight cycle. So this is the main thing that needs proof. Okay, and that's the algorithm. So the claim is that at the end, we should have d of v, let's say else, so to speak, d of v equals delta of s comma v for every vertex v. If we don't find a negative weight cycle according to this rule, then we should have all the shortest path weights. That's the claim. Now, first question is, here the running time is very easy to analyze, so let's start with the running time. We can compare it to Dijkstra, which is over here. What is the running time of this algorithm? V times E, exactly. Okay, I'm going to assume, because it's pretty reasonable, that V and E are both positive. Then it's V times E. So this is a little bit slower, or a fair amount slower than Dijkstra's algorithm. There it is. E plus V log V is essentially, ignoring the logs is pretty much linear time. Here we have something that's at least quadratic in V, assuming your graph is connected. So it's slower, but it's going to handle these negative weights. Dijkstra can't handle negative weights at all. So let's do an example, make it clear why you might hope this algorithm works. And then we'll prove that it works, of course. But the proof will be pretty easy. So I'm going to draw a graph that has negative weights but no negative weight cycles so that I get an interesting answer. Good. The other thing I need in order to make the output of this algorithm well-defined, it depends in which order you visit the edges. So I'm going to assign an arbitrary order to these edges. I could just ask you for an order, but to be consistent with the notes, I'll put an ordering on it. Let's say I put number 4 to say that's the 4th edge I'll visit. It doesn't matter, but it will affect how the algorithm, what happens during the algorithm for a particular graph. Get them all. 1, 2, 3, 4, 5, 6, 7, 8. Okay. And my source is going to be A. And that's it. So I want to run this algorithm. I'm just going to initialize everything. So I set the estimates for S to be 0 and everyone else to be infinity. And to give me some notion of time, over here I'm going to draw or write down what the weights, what all of these d values are as the algorithm proceeds, because I'm going to start crossing them out and rewriting them. The figure will get a little bit messier, but we can keep track of it over here. So initially 0 and infinities. Yeah?
Do you have to go through the edges in the same order every iteration? Or?
It doesn't matter. So for the algorithm, you can go through the edges in different order every time, if you want. We'll prove that. But here I'm going to go through the same order every time. Good question. Turns out it doesn't matter here. Okay, so here's the starting point. Now I'm going to relax every edge. So there's going to be a lot of edges here that don't do anything. I try to relax edge -1. I say, well, I know how to get from S to B with weight infinity. Infinity plus 2, I can get to from S to E. Well, infinity plus 2 is not much better than infinity. Okay, so I don't do anything. Don't update this to infinity. I mean, infinity plus 2 sounds even worse, but infinity plus 2 is infinity. Okay, that's edge number 1. So no relaxation. Edge number 2, same deal. Edge number 3, same deal. Edge number 4, we start to get something interesting because I have a finite value here. It says I can get from A to B using a total weight of -1. So that seems good. Write down -1 here and update B to -1. The rest stay the same. So I'm just going to keep doing this over and over. That was edge number 4. Number 5, we also get a relaxation. 4 is better than infinity. So C gets a number of 4. Then we get to edge number 6. That's infinity plus 5 is worse than 4. Okay, so no relaxation there. Edge number 7. Edge number 7 is interesting because I have a finite value here, -1, plus the weight of this edge, which is 3. That's a total of 2. Which is actually better than 4. So this route ABC is actually better than the route I just found a second ago. So this is now a 2. This is all happening in one iteration of the main loop. We actually found 2 good paths to C. We found one better than the other. Okay, and that was edge number 7. And edge number 8 is over here. It doesn't matter. Okay, so that was round 1. Of this outer loop. So the first value of I equals 1. Okay, now we continue. Just keep going. So we start with edge number 1. Now -1 plus 2 is 1. That's better than infinity. I'll start speeding up. This gets repetitive. It's actually not too much longer until we're done. Number 2 This is an infinity, so we don't do anything. Number 3, minus 1 plus 2 is 1, better than infinity. This is vertex D. And that's number 3. Number 4, we've already done, nothing changed. Number 5, this is where we see the path 4 again, but that's worse than 2, so we don't update anything. Number 6, 1 plus 5 is 6, which is bigger than 2, so no good to go around this way. Number 7, same deal. Number 8. Number 8 is interesting. So we have a weight of 1 here, a weight of minus 3 here, so the total is minus 2, which is better than 1. So that was D. And I believe that's it. So that was definitely the end of that round. So it's I plus 2, because we just looked at the 8th edge. And I'll cheat and check. Indeed, that is the last thing that happens. We can check the couple of outgoing edges from D, because that's the only one that whose value just changed. And there are no more relaxation possible. So that was in 2 rounds. Claim is we got all the shortest path weights. The algorithm would actually loop 4 times to guarantee correctness, because we have 5 vertices here and 1 less than that. So in fact, in the execution here, there are 2 more blank rounds. At the bottom, nothing happens, but what the hell? Okay, so that is Bellman-Ford. I mean, it's certainly not doing anything wrong. The question is, why does it converge? Why is it guaranteed to converge in B minus 1 steps unless there's a negative weight cycle? Question?
If you don't make any if you don't make any updates on one step, can you return and still? Because if you don't make any updates on one step, then you're not going to make it.
Right, so that's an optimization. If you discover a whole round and nothing happens, so you could keep track of that in the algorithm, then you can stop. In the worst case, it won't make a difference, but in practice, you probably want to do that. Yeah, good question. All right. So some simple observations. I mean, we're only doing relaxation, so we can use a lot of our analysis from before. In particular, the D values are only decreasing monotonically. As we cross out values here, we're always making them smaller, which is good. Another nifty thing about this algorithm is you can run it even in a distributed system. If this is some actual network, some computer network, and these are machines, and they're communicating via these links, I mean, it's a purely local thing. Relaxation is a local thing. You don't need any global strategy. And you're asking about, can we do a different order in each step? Well, yeah, you could just keep relaxing edges and keep relaxing edges and just keep going as for the entire lifetime of the network. And eventually you will find shortest paths. So this algorithm is guaranteed to finish in V rounds. In a distributed system, it might be more asynchronous and it's a little harder to analyze, but it will still work eventually. It's guaranteed to converge. And so Bellman-Ford is used a lot in like the internet for finding shortest paths. Okay, so let's finally prove that it works. So it should only take a couple of boards. So let's suppose we have a graph and some edge weights that have no negative weight cycles. Then claim is that we terminate with the correct answer. So Bellman-Ford terminates with all of these D of V values set to the delta values. For every vertex. Okay? Proof is going to be pretty immediate. Using the lemmas that we had from before, if you remember them. So we're just going to look at every vertex separately. So call the vertex V. Claim is that this holds by the end of the algorithm. So remember, what we need to prove is that at some point, d of v equals delta of s comma v, because we know it decreases monotonically, and we know that it never gets any smaller than the correct value, because relaxations are always safe. So we just need to show at some point this holds, and then it will hold at the end. So that's by So by monotonicity of the d values and by correctness part 1, which was that the d of these are always greater than or equal to the deltas. We only need to show that at some point we have equality. So that's our goal. So what we're going to do is just look at V and a shortest path to V and see what happens to the algorithm relative to that path. So I'm going to name the path. Let's call it P. Say it starts at vertex V0, goes to V1, V2, whatever, and ends at VK. And this is not just any shortest path, but it's one that starts at S, so V0 is S, and it ends at V. So I'm going to give a couple of names to S and V so I can talk about the path more uniformly. So this is a shortest path. From S to V. Now I also want it to be not just any shortest path from S to V, but among all shortest paths from S to V, I want it to be one with the fewest possible edges. Okay, so shortest here means in terms of the total weight of the path. Subject to being shortest in weight, I want it to also be shortest in the number of edges. And the reason I want that is to be able to conclude that P is a simple path, meaning that it doesn't repeat any vertices. Now, can anyone tell me why I need to assume that the number of edges is the smallest possible in order to guarantee that P is simple? Claim is that not all shortest paths are necessarily simple. Yeah?
Because you can have a loop that has weight 0.
Right, I could have a 0 weight cycle. Exactly. So we're hoping, I mean, in fact, in the theorem here, we're assuming that there are no negative weight cycles, but there might be 0 weight cycles still. If there's a 0 weight cycle, you can put that in the middle of any shortest path, make it arbitrarily long, repeat vertices over and over. That's going to be annoying. What I want is that P is simple. And I can guarantee that essentially by shortcutting. If ever I take a 0 weight cycle, I throw it away. And this is one mathematical way of doing that. Okay. Now, what else do we know about this shortest path? Well, we know that subpaths of shortest paths are shortest paths. That's optimal substructure. So we know what the shortest path from S to VI is. Sort of inductively, it's the shortest path. I mean, it's the weight of that path, which is in particular the shortest path from S to V minus 1 plus the weight of the last edge, V minus 1 to VI. So this is by optimal substructure, which we proved last time. Okay, and I think that's pretty much the warm-up. So I want to sort of do this inductively in I, start out with V0 and go up to VK. So the first question is, what is D of V0, which is S? Okay, what is D of the source? Well, certainly at the beginning of the algorithm it's 0. So let's say equals 0 initially, because that's what we set it to, and it only goes down from there, so certainly at most 0. The real question is, what is delta of S comma v0. What is the shortest pathway from S to S?
It has to be 0, otherwise you have a negative weight cycle.
It has to be 0, otherwise you have a negative weight cycle. Exactly. Okay, my favorite answer, 0. Okay, so from our, if we had another path from S to S, that is the cycle. So it's got to be 0. So these are actually equal at the beginning of the algorithm, which is great. That means they will be for all time, because we just argued up here, only goes down, never can get too small. So this is, we have d of v0 is set to the right thing. Great. Good for the base case of the induction. Of course, what we really care about is vk, which is v. So let's talk about vi inductively, and then we will get vk as a result. So, yeah, let's do it by induction. That's more fun. Let's say that d of vi is equal to delta of s vi after I rounds of the algorithm. So this is actually referring to the I that is in the algorithm here. These are rounds. So one round is an entire execution of all the edges, relaxation of all the edges. So this is certainly true for I equals 0. We just proved that. After 0 rounds, at the beginning of the algorithm, d of v0 equals delta of SV0. Okay, so now, yeah, it's not really what I wanted, but okay, fine. Now we'll prove it for d of vi plus 1. Generally, I recommend you assume something. In fact, why don't I follow my own advice and change it? It's usually nicer to think of induction as recursion. So you assume that this is true, let's say, for j less than the I that you care about, and then you prove it for d of vi. It's usually a lot easier to think about it that way. In particular, you can use strong induction. Assume it for all j less than I. Here, we're only going to need it for 1 less. Okay, so we have some relation between I and I minus 1 here in terms of the deltas. And so we want to argue something about the d values. Okay. Well, let's think about what's going on here. We know that, let's say, after I minus 1 rounds, we have this inductive hypothesis, d of vi minus 1 equals delta of s vi minus 1. And we want to conclude that after I round. So we have one more round to do this. We want to conclude that d of vi has the right answer, delta of s comma vi. Does that look familiar at all? So we're going to relax every edge in this round. In particular, at some point, we have to relax the edge from vi minus 1 to vi. We know that this path consists of edges. That's the definition of a path. So during the ith round, we relax every edge. So we better relax vi minus 1 vi. And what happens then? It's a test of memory. Quick, the Death Star is approaching. So if we have the correct value for vi minus 1, then we relax an outgoing edge from there. And that edge is an edge of the shortest path from S to vi. What do we know?
d of vi becomes delta of s vi.
d of vi becomes the correct value, delta of s comma vi. This was called correctness lemma last time. One of the things we proved about Dijkstra's algorithm, but it was really just a fact about relaxation. And it was a pretty simple proof. And it comes from this fact. We know the shortest path weight is this, so certainly d of vi was at least this big. And let's suppose it's greater, otherwise we were done. We know that d of vi minus 1 is set to this, and so this is exactly the condition that's being checked in the relaxation step. And they will actually, the d of vi value will be greater than this, let's suppose. And then we'll set it equal to this, and that's exactly d of svi. So when we relax that edge, we've got to set it to the right value. So this is the end of the proof, right? Very simple. The point is, you look at your shortest path. Here it is. And if we assume there's no negative weight cycles, this has the correct value initially. D of s is going to be 0. After the first round, you've got to relax this edge, and then you get the right value for that vertex. After the second round, you've got to relax this edge, which gets you the right value, d value for this vertex, and so on. And so no matter which shortest path you take, you can apply this analysis, and you know that if the length of this path is, here we assumed it was k edges, then after k rounds, you've got to be done. Okay, so this was not actually the end of the proof, sorry. So this means after k rounds, we have the right answer for vk, which is v. So the only question is, how big could k be? And it better be the right answer, at most v minus 1. It's the claim by the algorithm that you only need to do v minus 1 steps. And indeed, the number of edges in a simple path in a graph is at most the number of vertices minus 1. K is at most v minus 1 because p is simple. So that's why we had to assume that it wasn't just any shortest path, it had to be a simple one, so it didn't repeat any vertices. So there are at most v vertices in the path, so at most v minus 1 edges in the path. Okay? And that's all there is to Bellman-Ford. So pretty simple in correctness. Of course, we're using a lot of the lemmas that we proved last time, which makes it easier. Okay, a consequence of this theorem, or of this proof, is that if Bellman-Ford fails to converge, and that's what the algorithm is checking, is whether this relaxation still requires work after these v minus 1 steps, right? The end of the algorithm is run another round, a vth round, see whether anything changes. So we'll say that the algorithm fails to converge after v minus 1 steps, or rounds. Then there has to be a negative weight cycle. Okay, this is just the contrapositive of what we proved. We proved that if you assume there's no negative weight cycle, then we know that d of s is 0, and then all this argument says you've got to converge after v minus 1 rounds. Can't be anything left to do once you reach the shortest path weights, because you're going monothonically, you can never hit the bottom. You can never go through the floor. So if you fail to converge somehow after v minus 1 rounds, you've got to have violated the assumption. The only assumption we made was there's no negative weight cycle. So this tells us that Bellman-Ford is actually correct. When it says that there's a negative weight cycle, it means it. It's true. Okay. And you can modify Bellman-Ford in that case to sort of run a little longer and find where all the minus infinities are. And that is in some sense one of the things you have to do in your problem set, I believe. But I won't cover it here. But it's a good exercise in any case to figure out how you would find where the minus infinities are. What are all the vertices reachable from negative weight cycles? Those are the ones that have minus infinities. Okay, so you might say, well, that was awfully fast. Lecture's not over yet. Episode is not yet ended. We're going to use Bellman-Ford to solve even bigger and greater shortest paths problems. And in the remainder of today's lecture, we will see it applied to a particular, a more general problem in some sense called linear programming. And the next lecture will really use it to do some amazing stuff with all pairs shortest paths. Okay, but let's go over here. So our goal, although it won't be obvious today, is to be able to compute the shortest paths between every pair of vertices, which we could certainly do at this point just by running Bellman-Ford v times. Okay, but we want to do better than that, of course. And that will be the climax of the trilogy. Okay, today we just discover who Luke's father is. So it turns out the father of shortest paths is linear programming. Actually, simultaneously the father and the mother, because programs do not have gender. Okay. You know, my father likes to say, we both took improv comedy lessons. So we have degrees in improvisation. And he said that, we went to improv classes in order to learn how to, make our humor better. And the problem is it didn't actually make our humor better, it just made us less afraid to use it. So you're subjected to all this improv humor. I didn't see the connection to Luke's father, but there you go. Okay, so linear programming is a very general problem, very big tool. Has anyone seen linear programming before? Okay, no one person. Okay, and I'm sure you will at some time in your life. Do anything vaguely computing optimization related, linear programming comes up at some point. Very useful tool. You're given a matrix and two vectors. Okay, not too exciting yet. What you want to do is find a vector. Okay, this is a very dry description. We'll see what makes it so interesting in a moment. So you want to maximize some objective, and you have some constraints. And they're all linear. So the objective is a linear function in the variables x, and your constraints are a bunch of linear constraints, inequality constraints. That's what makes it interesting. It's not just solving a linear system, as you've seen in linear algebra or whatever. Or, of course, it could be that there's no such x. Okay, vaguely familiar, you might think, to the theorem about Bellman-Ford. And we'll show there's some kind of connection here, that either you want to find something or show that it doesn't exist. Well, that's still a pretty vague connection. But also want to maximize something or sort of minimizing shortest paths. Okay, looks somewhat similar. We have these constraints. So, yeah, this may be intuitive to you. I don't know. I prefer a more geometric picture, and I will try to draw such a geometric picture, and never tried to do this on a blackboard, so it should be interesting. I think I'm going to fail miserably. Sort of looks like a dodecahedron, right? Sort of, kind of, not really. A bit rough on the bottom. Okay, so you have if you have a bunch of linear constraints, this is supposed to be in 3D. Okay, now I labeled it, it's now in 3D. Good. So you have these linear constraints, that turns out to define hyperplanes in n dimensions. Okay, so you have space. Here is three-dimensional space, so n equals 3. And these hyperplanes, if you're looking at one side of the hyperplane, that's the less than or equal to, you take the intersection, you get some convex polytope or polyhedron. In 3D, you might get a dodecahedron or whatever. And your goal, you have some objective vector c, let's say up. Suppose that's the c vector. Your goal is to find the highest point in this polytope. So here it's maybe this one. Okay, this is the target. This is the optimal x. That is the geometric view. If you prefer the algebraic view, you have you want to maximize this c transpose times x. So this is n. This is n. Check out the dimensions work out. So that's saying you want to maximize the dot product. You want to maximize the extent to which x is in the direction c. And you want to maximize that subject to some constraints, which looks something like this, maybe. So this is a, and it's m by n. You want to multiply it by, should be something of height n. That's x. Let me put x down here. And by 1. And it should be less than or equal to something of this height, which is b, the right-hand side. Well, b, n. Okay, that's the algebraic view, just to check out all the dimensions are working out. But you can read these off, and each row here, when multiplied by this column, gives you one value here, and that's just a linear constraint on all the xi's. So x, you want to maximize this particular linear function of x1 up to xn, subject to these constraints. Okay, pretty simple, but pretty powerful and general. So it turns out that with you can formulate a huge number of problems, such as shortest paths, as a linear program. So it's a general tool. And in this class, we will not cover any algorithms for solving linear programming. It's a bit tricky. I'll just mention that they're out there. Say there's many efficient algorithms and lots of code that does this. It's a very practical setup. So lots of algorithms to solve LPs, linear programs. Linear programming is usually called LP. And I'll mention a few of them. There's the simplex algorithm. This is one of the first. There's, I think it is the first, the ellipsoid algorithm. There's interior point methods. And there's random sampling. I'll just say a little bit about each of these, because we're not going to talk about any of them in depth. The simplex algorithm, this is, one of the first algorithms in the world in some sense, certainly one of the most popular. It's still used today. Almost all linear programming code uses the simplex algorithm. Happens to run an exponential time in the worst case, so it's actually pretty bad theoretically. But in practice, it works really well. And there's some recent work that tries to understand this, but still exponential in the worst case. But it's practical. There's actually an open problem whether there exists a variation of simplex that runs in polynomial time, but won't go into that. That's a major open problem in this area of linear programming. The ellipsoid algorithm was the first algorithm to solve linear programming in polynomial time. So for a long time, people didn't know. Around this time, people started realizing polynomial time is a good thing. That happened around late 60s. Polynomial time is good. And the ellipsoid algorithm was the first one to do it. It's a very general algorithm, very powerful theoretically, completely impractical. But it's cool. It lets you do things like you can solve a linear program that has exponentially many constraints in polynomial time. All sorts of crazy things. So I'll just say it's polynomial time. No, can't say something nice about it. Don't say it at all. Okay, it's impractical. Interior point methods are sort of the mixture. They run in polynomial time, you can guarantee that. And they're also pretty practical. And there's sort of this competition these days about whether simplex or interior point is better. And I don't know what it is today, but a few years ago they were neck and neck. And random sampling is a brand new approach. This is just from a couple years ago by two MIT professors, Dimitris Bertsimas and Santosh Vempala. Both, one's in EE, I guess, and the other is in applied math. So just to show you, there's active work in this area. People are still finding new ways to solve linear programs. This is completely randomized and very simple and very general. Hasn't been implemented, so we don't know how practical it is yet, but has potential. Okay, pretty neat. Okay, we're going to look at a somewhat simpler version of linear programming. The first restriction we're going to make is actually not much of a restriction, but nonetheless we will consider it. A little bit easier to think about. So here we had some polytope we wanted to maximize some objective. In a feasibility problem, I just want to know, is the polytope empty? Can you find any point in that polytope? Can you find any set of values x that satisfy these constraints? Okay, so there's no objective. C, just find x such that ax is less than or equal to b. Okay, turns out you can prove a very general theorem that if you can solve linear feasibility, you can also solve linear programming. Won't prove that here, but this is actually no easier than the original problem, even though it feels easier, and it's easier to think about. I'm just saying actually no easier than LP. Okay, the next restriction we're going to make is a real restriction and simplifies the problem quite a bit. And that's to look at difference constraints. And if all this seemed a bit abstract so far, we'll now ground ourselves a little bit. So a system of difference constraints is a linear feasibility problem. So it's an LP where there's no objective. And it's with a restriction. So where each row of the matrix so the matrix A has 1, 1, and it has 1 minus 1, and everything else in the row is 0. Okay, in other words, each constraint has this very simple form. It involves two variables and some number. So we have something like xj minus xi is less than or equal to wij. So this is just a number. These are two variables. There's a minus sign. No values up here, no coefficients. No other of the xk's appear. Just two of them. And you have a bunch of constraints of this form, one per row of the matrix. Geometrically, I haven't thought about what this means. I think it means the hyperplanes are pretty simple. Sorry, I can't do better than that. It's a little hard to see this in high dimensions. But it will start to correspond to something we've seen, namely the board that it's next to, very shortly. Okay, so let's do a very quick example, mainly to have something to point at. So here's a very simple system of difference constraints. Okay, and a solution. Why not? Not totally trivial to solve this, but here's a solution. And the only thing to check is that each of these constraints is satisfied. x1 minus x2 is 3, which is less than or equal to 3, and so on. So there could be negative values, there could be positive values. Doesn't matter. Okay, I'd like to transform this system of linear of difference constraints into a graph, because we know a lot about graphs. So I'm going to call this the constraint graph. And it's going to represent these constraints. How do I do it? Well, I take every constraint, which in general looks like this, and I convert it into an edge. Okay, so if I write it as xj minus xi less than or equal to some wij, w seems suggestive of weights. That's exactly why I called it w. I'm going to make that an edge from vi to vj, so the order flips a little bit. And the weight of that edge is wij. So just do that. In other words, make n vertices. So you have number of vertices equals n. Number of edges equals the number of constraints, which is m, the height of the matrix. And just transform. So for example, here we have 3 variables. So we have 3 vertices, v1, v2, v3. We have x1 minus x2, so we have an edge from v2 to v1 of weight 3. We have x2 minus x3, so we have an edge from v3 to v2 of weight minus 2. And we have x1 minus x3, so we have an edge from v3 to v1 of weight 2. Make sure I got the directions right. Yep. So there it is, a graph. Currently no obvious connection to shortest paths, right? But in fact, this constraint is closely related to shortest paths. So let me just rewrite it. You could say, well, xj less than or equal to xi plus wij. Or you could think of it as dj less than or equal to di plus wij. Just this conceptual balloon. Look awfully familiar. A lot like the triangle inequality, a lot like relaxation. So there's a very close connection between these two problems, as we will now prove. So, I'm going to have 2 theorems, and they're going to look similar to the correctness of Bellman-Ford in that they talk about negative weight cycles. So here we go. Turns out, we have this constraint graph that can have negative weights, it can have positive weights. Turns out what matters is whether you have a negative weight cycle. So the first thing to prove is that if you have a negative weight cycle, then something bad happens. Okay, what could happen bad? Well, we're just trying to satisfy this system of constraints. So the bad thing is there might not be any solution. These constraints may be infeasible. And that's the claim. The claim is this is actually an if and only if. But first we'll prove the if. If you have a negative weight cycle, you're doomed. The difference constraints are unsatisfiable. That's a more intuitive way to say it. In LP world, they call it infeasible. But unsatisfiable makes a lot more sense. There's no way to assign the xi's in order to satisfy all the constraints simultaneously. So let's just take a look. consider a negative weight cycle. Starts at some vertex, goes through some vertices, and at some point comes back. I don't care whether it repeats vertices, just as long as this cycle from V1 to V1 is a negative weight cycle. Strictly negative weight. Okay, and what I'm going to do is just write down all the constraints. Each of these edges corresponds to a constraint, which must be in the set of constraints because we had that graph. So these are all edges. Let's look at what they give us. So we have an edge from V1 to V2. That corresponds to x2 minus x1 is at most something, W12. Then we have x3 minus x2. It's the weight W23, and so on. And eventually we get up to something like xk minus xk minus 1. So that's sort of that's this edge. Wk minus 1k. And lastly, we have this edge, which wraps around. So it's x1 minus xk. Wk1. Got the signs right? Good. So here's a bunch of constraints. What do you suggest I do with them? Anything interesting about these constraints, say the left-hand sides? Sorry? Sounded like the right word. What was it? Telescopes, yes, good. Everything cancels. If I added these up, there's an x2 and a minus x2. There's an x minus x1 and an x1. There's an x minus xk and an xk. Everything here cancels if I add up the left-hand sides. So what happens if I add up the right-hand sides? So over here I get 0, my favorite answer. And over here we get all the weights of all the edges in the negative weight cycle, which is the weight of the cycle, which is negative. So 0 is strictly less than 0, contradiction. Contradiction, wait a minute. We didn't assume anything that was false. So it's not really a contradiction in the mathematical sense. We didn't contradict the world. We just said that these constraints are contradictory. In other words, if you picked any values of the xi's, there's no way that these could all be true, because then you would get a contradiction. So it's impossible for these things to be satisfied by some real xi's. So these must be unsatisfiable. Let's say there's no satisfying assignment. Be a little more precise. x1 up to xn. No way can we satisfy those constraints, because they add up to 0 on the left-hand side and negative on the right-hand side. Okay, so that's an easy proof. The reverse direction will be only slightly harder. Okay, so cool, we have this connection. So the motivation is, suppose you want to solve these difference constraints, and we'll see one such application. There's actually, I Googled around for difference constraints. There's a fair number of papers that care about distance constraints. And they all use shortest paths to solve them. So if we can prove a connection between shortest paths, which we know how to compute, and difference constraints, then we'll have something cool. And next class we'll see even more applications of difference constraints. Turns out they're really, really useful for all pairs shortest paths. Okay, but for now, let's just prove this equivalence, finish it off. So the reverse direction is if there's no negative weight cycle in this constraint graph, then the system better be satisfiable. So the claim is that these negative weight cycles are the only barriers for finding a solution. To these difference constraints. I have this feeling. So somewhere here. Oh, yeah, I did talk about the constraint graph. Good. Satisfiable. Good. So here we're going to see a technique that is very useful when thinking about shortest paths. And it's a bit hard to guess, especially if you haven't seen it before. This is useful in problem sets and in quizzes and finals and everything, so keep this in mind. I'm using it to prove this rather simple theorem, but the idea of changing the graph, so I'm going to call this constraint graph G. Changing the graph is a very powerful idea. So we're going to add a new vertex S for source. Use the source, Luke. Okay. And we're going to add a bunch of edges from S, because being a source, it better be connected to some things. So we're going to add a zero weight edge, or weight zero edge, from S to everywhere. So to every other vertex in the constraint graph. Those vertices were called VI, V1 up to Vn. So I have my constraint graph. Let me copy this one so I can change it. Always good to back up your work before you make changes, right? There we go. So now I want to add a new vertex S over here, or my new source. I just take my constraint graph, whatever it looks like, add in weight zero edges to all the other vertices. Simple enough. Now, what did I do? What did you do? Well, I have a candidate source now which can reach all the vertices. So shortest paths from S, hopefully, well, paths from S exist. I can get from S to everywhere in weight at most zero. Okay. Maybe less. Could it be less? Well, yeah, like V2 I can get to by 0 minus 2. So that's less than 0. So I've got to be a little careful. What if there's a negative weight cycle? Oh, no. Then there wouldn't be any shortest paths. Fortunately, we assume there's no negative weight cycle in the original graph. And if you think about it, if there's no negative weight cycle in the original graph, we add S to an edge from S to everywhere else, we're not making any new negative weight cycles. Because you can start at S and go somewhere at a cost of 0, which doesn't affect any weights. And then you are forced to stay in the old graph. So there can't be any new negative weight cycles. So this graph, so the modified graph, has no negative weight cycles. That's good, because it also has paths from S, and therefore it has shortest paths from S. So modified graph has no negative weight cycles, because it didn't before, and it has paths from S. And there's a path from S to every vertex. There may not have been before. Before I couldn't get from V2 to V3, for example. That's still true. But from S I can get to everywhere. So that means that this graph, this modified graph, has shortest paths. Shortest paths exist from S. In other words, if I took all the shortest path weights, like I ran Bellman-Ford from S, then I would get a bunch of finite numbers, d of v, for every value, for every vertex. That seems like a good idea. Let's do it. So shortest paths exist. Let's just assign xi to be the shortest path weight from S to vi. Okay, so this. Why not? That's a good choice for a number. The shortest pathway from S to Vi. This is finite because it's less than infinity and it's greater than minus infinity. So So some finite number, that's what we need to do in order to satisfy these constraints. The claim is that this is a satisfying assignment. Why? Triangle inequality. Somewhere here we wrote triangle inequality. This looks a lot like the triangle inequality. In fact, I think that's the end of the proof. Let's see here. What we want to be true with this assignment is that xj minus xi is less than or equal to wij whenever ij is an edge, or let's say vi, vj, for every such constraint. So for vi, vj in the edge set. Okay, so when is this true? Well, let's just expand it out. So xi is this delta, and xj is some other delta. So we have delta of s vj minus delta of s vi. And on the right-hand side, well, wij, that was the weight of the edge from I to j. So this is the weight of vi to vj. Okay, I will rewrite this slightly. Delta of s vj is less than or equal to delta of s vi plus w of vi vj. And that's the triangle inequality, more or less. Shortest path from S to Vj is at most shortest path from S to Vi plus a particular path from Vi to Vj, namely the single edge Vi to Vj. This can only be longer than the shortest path, and so that makes the right-hand side bigger, which makes this inequality more true. Okay? Meaning it was true before, and now it's still true. And that proves it. This is true, and these were all equivalent statements. This we know to be true by triangle inequality. Therefore, these constraints are all satisfied. Magic. I'm so excited here. So we've proved that having a negative weight cycle is exactly when these system of difference constraints are unsatisfiable. So if we want to satisfy them, if we want to find the right answer to x, we run Bellman forward. Either it says, oh, no negative weight cycle. Then you're hosed, then there's no solution. But that's the best you could hope to know. Otherwise, it says, oh, there was no negative weight cycle, and here are your shortest path weights. You just plug them in, and bam, you have your xi's that satisfy the constraints. Awesome. Now, it wasn't just any graph. I mean, we started with constraints, algebra. We converted it into a graph by this transform. Then we added a source vertex S. So, I mean, we had to build a graph to solve our problem. Very powerful idea. And then we just plug in Bellman forward. It gives us the answer. Cool. This is the idea of reduction. You can reduce the problem you want to solve into some problem you know how to solve. We know how to solve shortest paths when there are no negative weight cycles, or find out that there is a negative weight cycle by Bellman forward. So now we know how to solve difference constraints. Turns out you can do even more. Bellman forward does a little bit more than just solve these constraints. But first let me write down what I've been jumping up and down about. The corollary is you can use Bellman forward you make this graph, then you apply Bellman forward, and it will solve your system of difference constraints. So let me put in some numbers here. You have m difference constraints, and you have n variables. And it will solve them in order m times n time. Actually, these numbers go up slightly because we're adding n edges and we're adding one vertex. But assuming all of these numbers are non-trivial, m is at least n. It's order mn time. Okay, trying to avoid cases where some of them are close to 0. Good. So some other facts, so that's what I just said. And we'll leave these as exercises because they're not too essential. The main thing we need is this. But some other cool facts is that Bellman forward actually optimizes some objective functions. So we were saying, oh, it's just a feasibility problem. We just want to know whether these constraints are satisfiable. In fact, you could add a particular objective function. So it won't, you can't give it an arbitrary objective function, but here's one of interest. x1 plus x2 plus xn. Okay, but not just that. We have some constraints. Okay, this is a linear program. I want to maximize the sum of the xi's, subject to all the xi's being non-positive and the difference constraints. So this we had before. This is fine. We noticed at some point that you could get from S to everywhere with cost at most 0. So we know that in this assignment, all of the xi's are negative. That's not necessary, but it's true when you run Bellman-Ford. So if you solve your system using Bellman-Ford, which is no less general than anything else, you happen to get non-positive xi's. And so subject to that constraint, it actually makes them as close to 0 as possible in the L1 norm, in the sum of these values. It tries to make the sum as close to 0. It tries to make the values as small as possible in absolute value, in this sense. Okay? It does more than that. It cooks, it cleans, it finds shortest paths. It also minimizes the spread, the maximum over all I of xi minus the minimum over all I of xi. So, I mean, if you have your real line and here are the xi's, wherever they are, it minimizes this distance. And 0 is somewhere over here. So it tries to make the xi's as compact as possible. This is actually the L infinity norm, if you know stuff about norms from your linear algebra class. Okay, and this is the L1 norm. I think it minimizes every norm, LP norm. Good. So let's use this for something. Yeah. Somewhere. Let's solve a real problem, and then we'll be done for today. Next class, we'll see the really cool stuff. It's a really cool application of all of this. For now, we'll see a cool but relatively simple application, which is VLSI layout. We talked a little bit about VLSI way back in Divide and Conquer. You have a bunch of chips, you want to arrange them and minimize some objectives. So here's a particular, there's tons of problems that come out of VLSI layout. Here's one of them. You have a bunch of features of an integrated circuit. You want to somehow arrange them on your circuit without putting any two of them too close to each other. You have some minimum separation, like at least they should not be on top of each other. Probably you also need some separation to put wires in between, and so on. So without putting any two features too close together. Okay, so just to give you an idea. So I have some objects, and I'm going to be a little bit vague about how this works. You have some features. This is stuff, some chips, whatever. We don't really care what their shapes look like. I just want to be able to move them around so that the gap at any point, so let me just think about this gap. This gap should be at least some delta, or I don't want to use delta. Let's say epsilon, good small number. So I just need some separation between all of my parts. And for this problem, I'm going to be pretty simple. Just say that the parts are only allowed to slide horizontally. So it's a one-dimensional problem. These objects are in 2D or whatever, but I can only slide them in x coordinate. So to model that, I'm going to look at the left edge of every part and say, well, these two left edges should be at least some separation. So I think of it as like whatever their distance is plus some epsilon. But if you have some funky 2D shapes, you have to compute, well, this is a little bit too close because these come into alignment. But there's some constraint. Well, for any two pieces, I could figure out how close they can get. They should get no closer. So I'm going to call this x1, call this x2. So we have some constraint like x2 minus x1 is at least d plus epsilon, or whatever you compute that weight to be, so ugly epsilon. Okay, so for every pair of pieces I can do this, compute some constraint on how far apart they have to be. And now I'd like to assign these x-coordinates. Right now I'm assuming they're just variables. I want to slide these pieces around horizontally in order to compactify them as much as possible so they fit in the smallest chip that I can make. Because it costs money and time and everything, and power and everything. You always want your chips small. So Bellman-Ford does that. All right, so Bellman-Ford solves these constraints. Because it's just a bunch of difference constraints. And we know that they're solvable because you could spread all the pieces out arbitrarily far. And it minimizes the spread. It minimizes the size of the chip I need, the max of xi minus the min of xi. So this is, it maximizes compactness, or minimizes size of the chip. Okay, this is a one-dimensional problem, so it may seem a little artificial, but the two-dimensional problem is really hard to solve. And this is, in fact, sort of the best you can do with a nice polynomial time algorithm. There are other applications if you're scheduling events in like a multimedia environment and you want to guarantee that this audio plays at least 2 seconds after this video, but then there are things that are playing at the same time and they have to be within some gap of each other. So lots of papers about using Bellman-Ford to solve difference constraints to enable multimedia environments. Okay, so there you go. And next class we'll see more applications of Bellman-Ford to all pairs shortest paths. Questions? Great.